Hello everyone, I'm Zoran Pirk and I will talk about our paper Modeling Long Horizon Tasks as Sequential Interaction Landscapes. In this work, our main goal was to enable robots to solve long horizon manipulation tasks. What is shown here is a robot controlled by our system performing a task, and the goal is to find two objects, a cup and a ball, to then put the ball in the cup and to move both objects together back into the cabinet. The cabinet door can also be closed, which means that the system has to deal with ambiguities and long-term planning to complete this task. The main motivation for our work was that many tasks are rather sequential and only shallow in their dependencies. That means we often need to carry out many steps to accomplish a task, but these steps do not necessarily depend on one another in a hierarchical way. And in turn, this means that there often exist many possible ways to accomplish a task or a goal. To learn the sequential structure of tasks with different possible orders, we define task-relevant actions that represent whether or not an object is set in motion. Each frame of a video sequence is labeled with an action symbol that defines whether or not an object is currently moving. Our goal is to understand the combinatorial landscape of how different actions can lead to the same outcome. In these examples, the same task is performed with different sequential orders of actions. In the left example, the purple block is put on top of the red block first, while for the right example, the yellow and the red block are put in place before the other blocks. Representing tasks as discrete action symbols allows us to reason about a task in more abstract ways, which has two advantages. First, we do not need to deal with the complexity of physics, which allows us to focus on the sequential structure of tasks. Second, we can use sequential models from natural language processing to efficiently learn and then predict long sequences of action symbols. So, to learn sequences of action symbols, we use a character-level sequence-to-sequence model that translates image embeddings to action symbols. Translating image embeddings to action symbols allows us to operate a robot in a closed-loop setting, where we are still able to predict action symbols over long time horizons. When we predict a sequence to execute tasks, the idea is to use the predicted symbols to represent expert policies for subtasks. Each symbol represents a narrow skill that can be transferred and reused, and each of these policies now needs to deal with the complexity of the real world to manipulate objects. When we put all this together, we can define a symbol switching loop that predicts action symbols from image embeddings. This is the outer loop shown here. The second loop is a control loop that uses a predicted symbol to select a policy that enables the robot to perform a subtask. While the robot is performing the subtask, the outer symbol switching loop keeps predicting new action symbols depending on what is happening in the scene. For more details on these two loops, please refer to our paper. As we are predicting actions from image embeddings, a robot can adapt to changing conditions in the environment. Here we show how the system can adapt when the operator moves the ball back into the cabinet. The ball is put back in the cabinet and the sequence model again predicts to put the ball in the cup. In this situation, the robot first aims to find ball and cup, but because both objects are already combined in a meaningful way, our model just predicts a terminal symbol which indicates that the task is already completed. As a take-home message, we have introduced a novel framework that uses a sequential model to translate image embeddings to action symbols. Each task is represented by a discrete set of actions, where each action is performed continuously. We have shown that action symbols allow us to manage task complexity over long time horizons, as well as task ambiguity, for example when objects are hidden. Finally, we have shown that action symbols can be used to select LFD or RL policies that represent narrow skills to perform complex subtasks. This concludes my talk. Thank you.